A rail bridge stretching 5.8 miles across open water in Louisiana. Concrete tunnels shoved sideways beneath live tracks. Crossovers worth $1.5 million swapped in 24 hours. The world's rail networks are being built and rebuilt every night, and the passengers on the 6 a.m. train never notice. Here is how it actually works. Keep watching for a 1,500 kilonewton robot doing what once needed an entire crew. Most rail crews replace one side of the track at a time. This one does both at once. The R3 dual rail gang runs 85 railroaders and a line of specialty machines, laying about 1.5 track miles per day and hitting a record 310 miles of dual rail in a single year. But renewing the rails is nothing compared to rebuilding what sits underneath them, without ever shutting the line down. At Forcola in northern Italy, a temporary railway bridge spanning 18 meters was installed in just 7 hours during a scheduled closure. That bridge holds the track up so a 4,300-ton prefabricated underpass can be jacked in below while trains keep rolling. The rest of this video is basically one long answer to the question: how does something this heavy get rebuilt while it is still being used? Full renewal does not mean tearing everything up and starting from a blank slate. It means threading a complete construction sequence into the space between two rails. The process unloads new rails at night, strips the old fastening system off the ties, then pulls the ties themselves and drops in fresh ones. Old rails come out, new rails go in, and the crew moves straight into welding. Flash butt welds joining long sections and aluminothermic welds sealing the field joints where rails meet. Then the finishing sequence takes over. Grinding smooths every weld. Ballast gets unloaded, profiled, then tamped and leveled so the track sits true. A brushing pass cleans the surface, and dynamic stabilization compacts the ballast under simulated train weight so the geometry holds when real traffic returns. The step where a whole line has to wait is destressing. Heating and tensioning the rail so it stays neutral through summer expansion and winter contraction. Skip distressing, and you get to pick your season for the disaster. Here is where a whole train becomes a rolling factory. A track renewal train travels along the line, hauling stacks of concrete sleepers, and the machinery on board pulls old track apart at one end while laying new track behind it. All in a continuous sweep. Excavators strip the old rails and worn ties out of the ballast. Rail grinding heads throw sparks as they smooth the freshly laid rails. Workers in high visibility gear ride the train, feeding fasteners into position and checking alignment as the whole line advances. Break this sequence into separate crews and separate machines, and your overnight closure quietly becomes a 3-day PR problem. Every meter of finished track behind the train is a meter the operator can hand back to service, so the crew is racing their own timer, and usually winning by 20 minutes. Renewal is not always about pulling everything out. Sometimes the fix is what happens to the ballast already there. This specialized ballast handling machine scoops up the existing rock, moves it through a processing chain, and puts clean material back under the ties. All while staying on the track it is servicing. Now put that same renewal work on top of open water and see what happens. The Lake Pontchartrain Rail Bridge in Louisiana stretches 5.8 miles. The longest rail bridge over water in the world. The crew here is swapping around 1,400 crosties per mile on a 17-foot wide bridge in the middle of an actual lake. Barges catch the discarded ties. Rescue boats stand by. 70 degrees and calm at breakfast. 30-degree drop and 40-mile-per-hour winds by lunch. And out here, there is nothing to hide behind. When it turns, the whole gang packs out and comes back tomorrow. A kilometer of continuous rail does not arrive from the mill in one piece. It has to be built out of shorter sections joined so cleanly that trains never feel the connection. Flash butt welding is how that happens on the main line. The welding rig clamps down over the joint. Rams hold the two rail ends in precise alignment. Pulsed AC current at 600 to 700 amps flows through the contact zone, heating the steel to somewhere between 1,500 and 1,700 degrees Fahrenheit until the ends soften. Then hydraulic force pushes the rails together, fusing them into a single homogeneous piece. Excess metal squeezes out sideways and gets sheared off while still hot. The whole crew moves 1,400 feet down the line to the next joint and does it again. But the physics only works if the joint stays neutral through 100-degree temperature swings. Continuous welded rail expands in summer heat and contracts in winter cold, and a joint that ignored those forces would buckle in July or snap in January. The answer is a technique called destressing. Crews define a neutral temperature, usually somewhere around 25 degrees Celsius, where the rail sits force-free. When welding happens below that neutral point, say at 10 degrees, the rail is naturally shorter by around 6 centimeters over a 360-meter section. That gap has to be closed under tension, so the finished rail carries the correct built-in stress. An automated welding robot can pull the rails together with up to 1,500 kilonewtons of force and up to 250 millimeters of travel. Alignment, tensioning, and welding all run in a single programmed sequence, and the machine holds the rail fixed until the joint cools enough to lock in the built-in tension. The alternative was demonstrated decades ago with mobile flash butt welding rigs. They automated the weld itself, but every alignment and every tension check still needed hands. Modern robots collapsed both into one process. The upside is quality. No foreign filler material means the joint is homogeneous, with no hardness discontinuity at the weld. The weld sitting under your train tonight was probably poured by 2 people who have already forgotten which joint it was, and it will still be there when their grandkids ride the line. But not every joint sits on flat ground with a full rig on tow. Some welds happen at grade crossings, in switches, or in tight urban track where flash butt equipment cannot reach. And that is where thermite welding takes over. The crew clamps a ceramic mold around the rail ends. Molten metal from a chemical reaction between iron oxide and aluminum pours in at over 4,000 degrees Fahrenheit, filling the gap and fusing both rails into one piece. Then comes the hard part. Breaking down the mold while the metal is still workable, crimping off the excess from the top of the rail, and shaving the joint clean before the steel gets too hard to shape. The grinder rides both sides of the railhead, taking the weld back to the exact profile a wheel wants to see. Try leaving a bump the size of a fingernail up there. Every commuter within a mile is going to know exactly where it is. The field version of that process comes as a self-contained kit 2 people can carry to the joint. 2 workers in orange safety suits set up a pre-assembled aluminothermic welding system straight from the box. Jig, crucible, mold, all sized for the exact rail profile they are joining. The mold clamps around the joint. A sealing compound goes on to keep the molten metal from escaping. The crucible sits on top, loaded with the thermite mixture. Ignition sends a chemical reaction ripping through the powder, and within seconds, a stream of liquid steel at extreme temperature pours into the mold. The reaction produces its own bright orange glow. Once the pour is done and the metal has fused into the joint, the crew breaks off the excess, cleans up the surface, and moves on. 2 people, a metal box, and a chemical reaction hotter than lava. And the finished joint has to last longer than most careers on the railroad. Passengers see 2 rails. What actually holds the track in place is the crushed rock underneath. And over time, that rock stops doing its job. Ballast gets contaminated with dust, coal fines, dirt, and organic material. It gets crushed by decades of train weight. Water stops draining. The track starts to move. A deep ballast cleaning machine solves it in a single pass. The whole train straddles the line, excavating ballast from beneath the ties, running it through screens that separate reusable rock from fine contamination, and putting the cleaned material back in place. Workers monitor conveyor belts feeding the crushing and screening chambers as the machine moves. In some cases, a roll of geotextile fabric goes down between the subgrade and the fresh ballast, a filter that keeps the cleaning from having to be redone in 5 years. Once the ballast is clean, the track has to be put back into its exact geometric shape, and that is where mechanized sleeper laying takes over. Along yellow train halls, stacks of concrete sleepers along the freshly prepared bed, while a specialized car at the leading edge places them at precise spacing. Guide wires and sensors keep the alignment true. Workers ride the machine, feeding components and monitoring the placement head as it drops each sleeper exactly where it belongs. A front-end loader nearby handles the debris from the old track. The rate matters. Manual sleeper placement moves at a walking pace and burns crew hours. A dedicated laying machine can place hundreds per hour, so a closure window that used to swallow a full weekend collapses into a single overnight shift. After the sleepers are back, the track still sits slightly off from its target geometry, and that is what a leveling and tamping machine fixes. The equipment lifts the whole track structure, rails and ties together. A controlled amount off the ballast, adjusts the alignment sideways to the correct center line, then drives tamping tines down into the ballast on both sides of each tie. Those tines vibrate and squeeze rock underneath the sleepers, packing it tight where the track needs support. Then the machine finishes the ballast profile on top, leaving a clean surface that meets the design cross-section. The result is a track that sits exactly where the geometry drawings say it should. Level, straight where it should be straight, and curved to the correct radius where it should curve. Only after leveling and tamping comes the finishing pass, and this is where the track actually becomes usable again. A finishing machine runs green plows that shape the ballast profile, transverse brushes that sweep the tie surfaces clean, and a stabilizing unit that compacts the ballast around each sleeper. A high-pressure water spray washes the sleepers as the machine passes, and an integrated digital recorder logs the geometric results in real time, so the operator sees exactly what the track looks like behind them. The whole rig runs from an ergonomic cabin with joysticks and touchscreens. One operator controlling multiple workheads at once. The track you rode this morning was reshaped, cleaned, and measured last night, and nobody sent you a memo. Zoom out, and this is not a few isolated machines. It is an entire industrial ecosystem. Cleaners, layers, tampers, ballast processors, catenary equipment, cranes. Designed to keep a massive rail network alive without ever really stopping it. Which raises the next question. If speed keeps going up, is loose ballast still the right foundation at all? High-speed lines push the whole system past what loose ballast was designed to handle. On this East European high-speed project, crews are delivering 2,000 concrete sleepers a day, laying 1,666 per kilometer, and installing continuous welded rail up to 404 meters long in a single feed. A gravel-spreading truck lays 2 parallel strips along the track bed. Sleepers get stacked in groups of 40 every 24 meters. A specialized rail-laying train pulls the long, welded rail into place while a spider shovel guides it onto the sleepers, and the fast-clip fastening system locks it down. And here is what replaces loose ballast at high speed. Slab-track. Precast concrete panels bolted straight onto a prepared base, with the rails fastened directly to the concrete. The pavement milling machine cleans off the old surface. Graders, rollers, and water trucks prepare the underlying track bed to millimeter precision. Then the precast slabs get lifted into position, aligned with surveying equipment, and secured. Rails go on top, fastened directly to the concrete instead of sitting on wooden or concrete ties. Imagine your local interstate getting tamped and reshaped every few months. That is the ballast tax. Slab-track pays it once, up front, and walks away. The mature version of Slab-track is engineered as a complete system. Precast concrete panels, typically 5.16 meters long and 2.4 meters wide. Get manufactured to visible concrete finish quality in a controlled factory environment, with an elastic layer bonded underneath each panel to dampen vibration. On site, the panels are placed to a tolerance of plus or minus 0.5 centimeters and locked in with self-compacting grout that hardens fast enough to allow trains within a short curing window. If a damaged section ever needs replacement, a 50-meter stretch can be swapped and returned to service in around 10 hours. A derailment in the morning, running trains again by dinner. Building a new high-speed line on open ground is one problem. Rebuilding a metro line while a city keeps using it every morning is a different one entirely. Rome's Metro Line A is being renewed across 25 kilometers of track, and every hour of work happens at night after the last train. Crews cut out old rails with torches, strip old ballast with conveyor belt wagons, and drop in fresh concrete sleepers under floodlights. A tamping machine compacts the new ballast while brushing equipment levels the surface. The clock is not something the crew has to work around. The clock is the entire job description. Then it gets even harder. At Baldo degli Ubaldi station, the crew is not just replacing ballast. They are swapping the entire track structure over to a ballastless system while the service resumes each morning. Old track and ballast come out during the overnight window. Precast concrete slabs get lifted in and aligned to a laser level. Grout gets mixed on site and cast in place. New rails go down on top with final checks by laptop and surveying instruments. And by sunrise, trains are running. Now put that same overnight rhythm inside one of the busiest railway environments in Europe. Roma Termini handles enormous passenger traffic through dozens of parallel tracks, and the renewal work here has to happen track by track without shutting the station down. Excavators pull the old rails out with grapples. Rebar cages get lowered into position. A concrete pump truck pours the base layer. Then, a specialized delivery train brings prefabricated slabs directly onto the work zone, and a crane system places each one to millimeter tolerance. New rails go on top, alignment gets checked, fastenings get torqued down. The track that carried service 2 nights ago is a different track today. Tell me which metro or main station in your city you think handles overnight work the best. The step where the whole line has to wait is the concrete cure time. Get the grout formula wrong, and the 6 a.m. commuters find out before your boss does. Renewal is not always about the rails you can see. Sometimes it is about what protects the bridge underneath them. At the Pausen Viaduct in the Ardèche region of France, crews are renewing 2 kilometers of track and re-waterproofing the deck of 2 elevated structures at the same time. 50 to 60 workers rotate through shifts up to 6 days a week. The site has no road access to the viaduct itself, so 2 work trains supply both the track renewal and the waterproofing crews. When your only mailing address is the track, everything you need, including the crew's lunch, arrives on rails. And here's the trick that lets road underpasses get built directly beneath live railway lines. The structure gets cast at ground level next to the track. Then hydraulic cylinders push it sideways, through the earth beneath the rails, while trains keep running overhead at reduced speed. Temporary shoring under the rails takes the load while the concrete underpass slides into its final position. The soil ahead gets excavated as the structure advances. Hydraulic pressure transfers through a reaction wall and directly into the ground. Once the box reaches its target, ballast gets poured back on top, and the track gets tamped, profiled, and returned to full service speed. The road underpass is now permanent, and the trains never stopped. Commuters riding across the top had no idea a tunnel was being shoved into the ground beneath them all morning. The moment a new track opens for service, wear begins. Every wheel that passes reshapes the rail surface a little more. A rail grinder rolls through at night, throwing sparks as controlled grinding wheels remove a precise layer of steel, restoring the exact profile a wheel needs to see. But the track is not just wearing out from above. The corridor around it is closing in from the sides. Vegetation grows into the right-of-way. Grass, brush, small trees, blocking sightlines, hiding defects, and creating a fire hazard next to active rails. A rail-mounted brush cutter with a saw head attachment handles both. The 260 horsepower machine runs a heavy cutting arm out to the side of the track, taking down medium trees, branches, and tall grass in a single pass. Same base machine also handles snow plowing and ballast work in other seasons. Cheaper to buy 1 machine and swap the head than to buy 3 machines and pay for 3 garages. And here is the elegant answer to reaching remote track: a railroad excavator. The machine drives on regular roads to get near the work zone, then transitions onto the rails and moves along the corridor like any other maintenance-of-way vehicle. A mulching attachment on the boom clears vegetation to the side while ground crews with brush cutters finish the areas the machine cannot reach. 2 travel modes, 0 low-loader trucks, and 1 less headache for the site supervisor. When vegetation control gets skipped for years, the maintenance turns into a full clearing campaign. At the BGRM Mainline Rehabilitation Project, an orange dual-head cutter had to work its way through 5.5 miles of track that had gone untended for so long, the surrounding forest was crowding both sides of the line. Several passes of the machine were needed just to open the corridor back up. The dual heads cut simultaneously on both sides, chewing through overgrowth that had built up into dense walls of brush and small trees. The point of doing this is not cosmetic. A closed-in corridor means inspectors cannot see the ballast condition. Drainage stops working, wildlife starts using the tracks as cover, and any defect on the railhead becomes invisible until a train finds it. Skip a few maintenance seasons, and the track is no longer overgrown. The forest just owns it now, and you rent. The most dangerous rail defects are the ones that never surface. Cracks grow inside the steel of a crossing point where wheels transfer between rails, invisible to the eye. Synthetic aperture focusing technique uses ultrasonic waves to scan the full volume of the steel and catch flaws before they become failures. Now scale defect prevention up to the second largest rail network on the planet. A specialized track cleaner train lifts the ballast, washes the rock, redistributes it between and around the ties, then tamps it back down to hold the track in position. Kilometers of maintenance per shift. With 139,000 kilometers of rail, including 35,000 kilometers of high-speed line, inspection cannot rely on hands and eyes alone. Ballast tamping machines, rail-mounted cutters, and manual crews all work in coordinated cycles. The best repair is the one you never had to make, because somebody found the crack 6 months before it wanted to become news. A straight track is a wheel following a line. A turnout is where geometry gets hard. At Forest Field in Western Australia, crews installed a $1.5 million double dual-gauge turnout, a crossover that handles 2 different track gauges on the same alignment, during a 24-hour shutdown. The pre-assembled concrete sleeper base gets set. Rails are welded in with sparks flying under lights. Wheel loaders spread and shape ballast. Workers use rail saws, thermite welding kits, and rail grinders to bring every joint into tolerance. A specialized maintenance vehicle rolls in for the final surfacing pass. Every component has to line up so precisely that trains crossing at speed feel nothing. 24 hours of work on Saturday for 50 years of service. And if you count the overtime, it is still the cheapest deal on the project. Sometimes the parts are too heavy and too awkward for a general-purpose crane. A dedicated track layer machine runs on its own crawlers, straddling the work zone and lifting entire turnout segments. The complex assemblies where 2 tracks split, straight from the flatbed onto the ballast. The crawlers rotate 45 or 90 degrees, so the machine walks sideways over rough ground while carrying a full turnout section suspended beneath its frame. Support legs adjust under load, letting it step around signal masts and existing catenary supports without setting the piece down. The center of gravity always stays between the crawlers, which is the difference between placing a turnout section and starring in the video everyone in the industry shares for the next 6 months. Radio control keeps the operator at a safe distance, watching from a spot where they can see both the load and the surrounding traffic clearances at the same time. Now do that same precision at scale, in a working freight corridor. At Worsley in Western Australia, crews replaced 585 crossover points with 60-kilogram tangential concrete turnouts, a design that lets trains cross between tracks at higher speed with less wear. The whole renewal, including relocating the crossover to a new position on the track, took just 16 hours. Excavators strip the old assembly. Front-end loaders spread fresh gravel. Pre-assembled turnout sections get lowered into place. Alignment gets surveyed, ballast gets compacted, and the finishing crew tamps everything back to spec. The work runs straight through into evening under machine floodlights. By the end of the closure window, a completely new crossover is in place, and the freight schedule the next morning does not skip a beat. Ask a freight operator what a crossover renewal costs, and the real answer is whatever their contract penalty would have been if the train stopped. And here is where turnout precision gets automated. 4 smart machines in Jiangsu, China work together to replace manual measurement and adjustment on high-speed rail turnouts. They collect data, analyze it, and make adjustments to 0.5 millimeter accuracy in just 3 rounds. Over 30% more efficient than crews. Here is a problem you never think about until you have to solve it. If the entire worksite is the track itself, how do you get the machines onto it? A dedicated ramp car, 70 feet of folding steel, deploys from a flatbed railcar and creates a 5.3% grade that maintenance of way equipment can drive down. No road access needed, no temporary construction site. The rail hauls the machine to the work site, then becomes the work site. Try getting that kind of turnaround out of a construction dumpster. And here is the same logic applied to raw materials. A specialized dump train hauls aggregate along the corridor and discharges it through a hydraulic boom at up to 2,000 tons per hour, placing ballast exactly where the crew needs it, including through significant curves. Each car has its own belt and drive system, moving material forward through the train to the transfer car at the end. The whole rig can be lengthened or shortened depending on the job. The railway spends its whole life carrying freight for everyone else, and then quietly delivers its own gravel on the side. The strangest thing about a railway is not that it runs hundreds of kilometers. It is that while thousands of trains pass over it every day, hundreds of machines underneath are quietly changing the very road those trains are running on. Which is exactly why the current push toward autonomous inspection drones, AI-driven defect prediction, and battery electric maintenance equipment matters so much. The network keeps growing, and so does the demand to service it without ever taking it offline. Freight operators in North America run trains up to 3 miles long with heavy axle loads, while European and Asian networks push short trains at very high speed. Which model do you think is easier to maintain long-term? The heavy freight approach or the high-speed passenger approach? Weigh in below. Tap that subscribe button if you want more deep looks at how heavy infrastructure actually works behind the scenes. Plenty more coming. See you. Take care.